There is a real number. Its first few digits are 1.30637778. If you raise this number to the third power, then take the floor, you get 2, a prime. If you raise it to the ninth power and take the floor, you get 11, another prime. Raise it to the 27th power, floor, 1361, prime. Raise it to the 81st power, take the floor, you get 2,521,008,887. That number is prime too. The exponents are 3, 9, 27, 81, powers of 3, and the claim is that this never breaks. For every positive integer n, the floor of a to the 3 to the n is a prime number. Not sometimes, not almost always, every single time, forever. This is not a pattern somebody noticed. It is a theorem. It was proven in 1947 by an American number theorist named William Hurwitz Mills in a paper that is exactly 1 page long. The number a is now called Mills' constant. At first glance, this is impossible. Primes are supposed to be unpredictable. We have been trying to find a formula for them for 2,000 years. Euclid could not find one. Gauss could not find one. The Riemann hypothesis, the most famous open problem in mathematics, is in some sense a question about how unpredictable primes are. And yet here is a single real number and a single floor function, and it prints primes forever. So what is going on? What is this number? Where did it come from? And if a formula for primes exists, why are we not all using it? The answers are strange and a little bit unsettling. Because Mills' theorem is true, the formula works. It really does produce infinitely many primes. But by the time we finish, you will understand why no mathematician considers this a formula for primes at all. In 1947, the Bulletin of the American Mathematical Society published a note by William Mills titled "A Prime Representing Function." The entire paper is 1 page. It has 2 paragraphs of prose, 1 display equation, and 3 citations. That is the whole thing. Mills was a professor at Yale at the time, and later at the Institute for Defense Analyses. He was 36 years old. The paper is almost a throwaway. He is not announcing a revolution. He is making a small, clever observation. But the observation turned out to be one of the most quoted results in the subject. Here is what Mills proved. There exists a real number a greater than 1 such that for every positive integer n, the floor of a raised to the 3 to the n is prime. That is it. That is the entire theorem. The first thing to notice is what the theorem does not say. It does not tell you what a is. It does not give a decimal expansion. It does not give an algorithm for computing a. It just asserts that such an a exists. This is what mathematicians call a non-constructive proof. Mills is not handing you the number. He is handing you a guarantee that a number with this property is out there somewhere in the real line and challenging you to find it. The second thing to notice is that the theorem says a real number a, not the real number a. There is no claim of uniqueness. In fact, as we will see, there are infinitely many valid choices. The smallest one is the number we now call Mills' constant. Its numerical value, 1.30637778 and so on, is only conjecturally the smallest. We do not know for certain, so Mills gave us 3 things: a promise that a prime printing constant exists, no formula for it, and no uniqueness. Why would anyone care? Why is this a celebrated result? Because of what Mills' trick reveals about existence proofs in number theory. The proof uses a classical result about prime gaps to chain primes together one after another, each one boxed inside a specific interval. The intervals shrink. A single real number falls into all of them. Albert Ingham, a number theorist at Cambridge, proved the following in 1937. For every sufficiently large integer n, there is a prime number strictly between n cubed and the cube of n plus 1. In other words, if you take any large number, cube it, and then cube the next number, the interval between those 2 cubes is never empty of primes. There is always at least 1 prime hiding inside. This is not obvious. Between n squared and n plus 1 squared, the gap is about 2n, and we believe but have not proven that there is always a prime in that interval. That is one of the oldest open problems in number theory, Legendre's conjecture. The cube version, the one Ingham proved, is easier but still very deep. Ingham actually proved something stronger. He showed that the gap between consecutive primes near a number x is always less than x to the 5/8 for x large enough. Cubing one side and comparing to the other, you can show that once n is big, the interval from n cubed to n plus 1 cubed is wider than x to the 5/8 and therefore contains a prime. This is the ingredient Mills needs, because it means he can play the following game. Start with any sufficiently large prime, call it p0. Then between p0 cubed and p0 plus 1 cubed, Ingham promises there is a prime, call it p1. Now cube p1. Between p1 cubed and p1 plus 1 cubed, Ingham again promises a prime, call it p2. Keep going. You get an infinite sequence of primes, p0, p1, p2, p3, and each one sits between the cube of the previous and the cube of the previous plus 1. This is a ladder, each rung is a prime. Each rung is trapped inside a cube-shaped cage built from the rung below. Ingham's theorem is the bolt that holds the ladder together. Once you have the ladder, you have almost everything you need. The rest is a trick with limits. Start with a prime. The classical starting point is 2. Cube it, you get 8. Between 8 and 27, Ingham says there is a prime. There is, many in fact. Pick one. To get the smallest Mills constant, we pick 11, because it leads to the tightest possible squeeze. Cube 11, you get 1,331. Between 1,331 and 1,728, there must be a prime. There is. The one we need is 1,361. Cube 1,361. You get roughly 2.52 billion, specifically 2,520,880,681. Between that number and the cube of 1,362, there is a prime. The specific one we need for Mills is 2,521,008,887. Now the numbers start to explode. The next term has 29 digits. It is 16 sextillion, 22 quintillion, 236 quadrillion, 204 trillion, 9,818,131,831, and so on. After a few more steps, the primes are hundreds of digits long. They grow triply exponentially. Each prime is roughly the cube of the one before. This is the ladder, 2, 11, 1,361, 2.5 billion, a 29-digit number, an 86-digit number, a 257-digit number. Every one of them prime, every one of them forced into existence by Ingham's theorem. Now here is Mills' trick. Take each prime p sub n and raise it to the 1/3 to the n, that is the 3 to the nth root. For p1 equals 11, the third root is about 2.22. For p2 equals 1,361, the ninth root is about 2.17. For p3, the 27th root, roughly 1.48. For p4, the 81st root, 1.32. These numbers are getting smaller, but not randomly smaller. They are getting smaller in a controlled way, and if you do the opposite, if you take the 3 to the nth root of p sub n plus 1 instead of p sub n, you get a slightly larger sequence approaching the same limit from above. The two sequences pinch together, they trap a real number between them. That real number is a, Mills' constant. Here is what just happened, slowly. Define u sub n to be p sub n raised to the 1/3 to the n. Define v sub n to be p sub n plus 1, the integer right after the prime, raised to the 1/3 to the n. Because each prime is squeezed between the cube of the previous and the cube of the previous plus 1, you can show that u sub n is an increasing sequence. Every term is a bit bigger than the last. Similarly, v sub n is a decreasing sequence, and u sub n is always less than v sub n. So we have an increasing sequence below, a decreasing sequence above, and they never cross. A classical theorem of real analysis, the monotone convergence theorem, says that both sequences must converge, and because the gap between them shrinks to 0, they converge to the same number. That number is a. Now here is the whole point. Plug a into the formula. Take a to the 3 to the n. Because u sub n is less than or equal to a, and a is less than v sub n, we can raise both sides to the power of 3 to the n. The left side becomes p sub n. The right side becomes p sub n plus 1, so p sub n is less than or equal to a to the 3 to the n, which is less than p sub n plus 1. That means the floor of a to the 3 to the n is exactly p sub n. And p sub n is prime by construction because we built the whole ladder out of primes. So the floor of a to the 3 to the n is prime for every n forever. Not because there is anything mystical about a, not because a has some magic number theoretic property. Just because a was defined to be the unique real number that lies inside an infinite nested sequence of intervals, and those intervals were built to contain primes. The formula is correct, the proof is airtight, and it is completely non-informative about what a actually is. Let us take stock of what we know about Mills' constant. We know it exists. We know the numerical value of the conjecturally smallest one, assuming the Riemann hypothesis, to about 6,850 decimal digits. That is a computation carried out by Chris Caldwell and Yuanyu Cheng in 2005. They did it by finding the primes on the ladder explicitly and then extracting enough digits of a to print them. That is basically the end of what we know. We do not know whether Mills' constant is rational. It is almost certainly irrational, but nobody has proven that. For comparison, we have known for 2,500 years that the square root of 2 is irrational. We have known for 260 years that e is irrational. We have known for 250 years that pi is irrational, but we do not know that Mills constant is irrational. We do not know whether it is transcendental. Transcendental means it is not the root of any polynomial with integer coefficients. Again, almost certainly yes. But unproven. We do not know a closed form for Mills constant, and this is not for lack of trying, it is because the only way we know how to define the number is by the sequence of primes it has to contain. There is no analytic identity, no integral, no infinite series, no continued fraction pattern that produces A. A is defined implicitly by its output. We do not even know for certain that 1.30637778 is the smallest valid Mills constant. That hinges on whether 2 is the smallest starting prime that yields a valid chain, and proving that requires Riemann hypothesis strength control over prime gaps that we do not yet have. So Mills constant is a real number we can compute to thousands of digits, whose existence we have proven, whose most basic properties we cannot determine. It is, in the strongest sense of the word, a strange number. If there is a formula that generates primes, why is it not the most important formula in computer science? Why does cryptography still rely on slow primality tests? Why is there still a prize for finding the next Mersenne prime? Why has Mills constant not changed the world? Because the formula is circular. To compute Mills constant to enough digits to extract the nth prime, you need to already know the first n primes on the Mills ladder. The prime p sub n has approximately 3 to the n times log 10 of a decimal digits. So to recover a 100-digit prime, you need to know a to 100 decimal places. And to know a to 100 decimal places, you have to first find a 100-digit prime inside a specific cube-sized interval, which is exactly the problem you were trying to solve. Mills constant does not help you find primes. Mills constant is a way of bottling primes you have already found. This is not unusual in the history of prime representing functions. It is in fact the rule. In 1670, John Wilson and Edward Waring noticed that a positive integer n is prime if and only if n-1 factorial is congruent to -1 modulo n. This is Wilson's theorem. It is a perfect primality test. It is also completely useless. Computing n-1 factorial is much harder than checking whether n is prime by any other method. In 1964, C.P. Willens wrote down a formula for the nth prime using Wilson's theorem and a pile of floor functions. The formula is closed form. You can type it into a computer, but evaluating it for even moderate n requires factorials of numbers the size of the primes you are hunting for. In 1976, Matiasevich, Davis, Putnam, and Robinson constructed a polynomial in 26 variables, of degree 25, whose positive values as the variables range over non-negative integers are exactly the prime numbers. This is stunning. It is an entire polynomial. And it is entirely impractical, because its values are almost always negative, and when they are positive, they correspond to primes that are already gigantic. Mills constant, Wilson's theorem, Willens' formula, Matiasevich's polynomial. 4 of the most famous prime representing functions in mathematics. None of them is an algorithm for finding primes. They are all elegant demonstrations that a closed-form description exists. They are not tools, they are monuments. Here is the real reason Mills constant matters. It is the clearest example in modern mathematics of a number we can point to, compute, and describe, but cannot understand. Compare it to the other famous constants. Pi is defined by a geometric relationship. We have proven it irrational. We have proven it transcendental. We know it satisfies no polynomial equation with integer coefficients. We can compute it by dozens of different methods that all agree. Pi is a number we understand. E is defined by a limit. It is the unique base of the natural exponential. It is the sum of the reciprocal factorials. It is the derivative of itself. We know it is irrational, transcendental, that it is normal in probably every base. E is a number we understand. The square root of 2 is the unique positive solution of x squared equals 2. We proved its irrationality in ancient Greece. Mills constant is not any of these. It is not defined by a geometric property. It is not the solution of an equation. It is not the sum of a series. It is defined as the unique real number that lies in an infinite nested sequence of intervals constructed to contain primes. We know it exists, we can print its digits, we cannot answer the most basic questions about what it is. This is not an anomaly. This is a recurring pattern in 20th century mathematics. Gödel's incompleteness theorems, Turing's undecidable problems, Chaitin's constant, all of these are results of the form we can prove this object exists, we can describe it in precise language, but we cannot penetrate it. Mills constant belongs to that family. It is a real number, as real as any number, hiding in plain sight at roughly 1.3063. It produces primes forever, and when we ask what kind of number it is, the mathematics has no answer. That is the strange beauty of Mill's theorem. It takes one of the deepest patterns in arithmetic, the distribution of primes, and reduces it to a single decimal expansion. It tells us, in one line, that such a decimal exists, and then it refuses absolutely to tell us anything else about it. We have the formula, we do not have the understanding, and the gap between those two things, the gap that Mills quietly exposed in 1947, is where most of modern mathematics lives.